Let me start the recording. Okay. So yeah, so this is the example that we're continuing. And in case you were not able to watch this synchronously now, if you're we started the recording a few minutes late, and this is what we have discussed. So let this slide also go on the record. That the number of places where we can start the matching run can also be visualized as diagonals of length 5 that you can put on a matrix, on this alignment matrix. All right, so, and the probability to get a single match was 1 over 20, right? So probability that a column is a match column. The probability to get 5 matching columns, consecutive matching columns, is going to be equal to 1 over 20 to the power 5. Okay, and you roughly multiply this with 1000 and 1000, ignoring those minus 5 plus 1. So this is roughly the expected number of matching runs of length 5. So I'm going to take out my cell phone and calculate this number. All right, so 1 over 20 is 0.04, right? Let me get, so actually we can directly run it on MATLAB or, yeah, let's do that. Octave Online. So 0.04, I think there's a power function, power 0.04 to the power 5. Is it going to work? Let's see. No, power, or yeah, I think this is it. The power function, I think this is of the correct number, 10 to the minus 7. So if you multiply this with, let's do the exact computation, plus 1 and 1000 minus 5 plus 1, 0.1. So the expected number of a matching run of length 5 between these two proteins is 0.1. So if somebody tells you that I found a matching run of length 5 between these two, it's something unexpected. Oh, 1 over 20 is 0.05. You're right. I actually, I treated like 25 amino acids. So let's correct that. Let's make it 0.05. So it's still 0.3. All right. So 1 over 20 is 0.05, right? Or, yeah, it should be like this, yeah. So 0.3, it's still unexpected, okay? I mean, what I mean is that observing something, the expected number is 0.3. It's not, I'm observing something, it may be a little bit surprising, maybe not too surprised. I mean, still the expected number is 0.3, it's less than 1. But when you observe a matching run of length 5, it may not be that surprising. It may not be that different from random, because what we have here, 0.3, is still not very close to 0. It's a large number here. So you may observe between two random amino acid sequences of 1000, you might, this is the expected value of a matching run of length 5. Now, I'm going to ask the question differently, the inverse question. Given the length of so what is the threshold that we should be surprised or not surprised? In other words, if I give you just the length of the proteins, for example, I have one protein of length 500 and the other protein is of length 300 amino acids, or let's have them DNA sequences. In DNA sequences, we are going to have 1 over 4 for a single match, and a length 5, for example, in this case, the probability is going to be much higher. All right. So if I have 2 DNA sequences of length 500 and 300 each, what is the threshold? I mean, what is the length? For example, is a length 8 of the matching run is expected, or 10, 15. So now we're asking, we are not trying to find the expected value for a specific length of matching run, but we're just given this and we are wondering what is the ratio, what is the threshold that, what is the length that in which the expected number of matching runs is going to be equal to 1, okay, in this case. So x is the random variable which tells me the number of matching runs that we expect between these two DNA sequences. In this case, that expected number we have computed was 0.3. So now I'm asking for which number this is 1. Because if you expect to see a 1 of that matching run, it means that that's the expected number. This is the length where you shouldn't get surprised at all. So we just need to work out our equations. So this, we're just going to set 1 is equal to 1 over 4 to the power length, whatever that length is, m minus l plus 1 times n minus l plus 1. So this is the place where this equation gets a little bit difficult, especially it's going to be much easier if you ignore l's here. So what I'm saying is that when we set 1 is equal to 1 over 4 to the power l times m and n, it will be much easier, right? I mean, we can take the logarithm of both sides, and then this will basically, here is the result that we're going to get, which is going to be this. So this is n is our, actually right here, yeah. So it's going to be, the expected number is going to be the logarithm base 1 over p and m times n. So this is what we did was, so this is exactly the same thing. So I set this one to 1. This is the expected number. This is the number of times we can try this. This is our probability of matching run of length L, where P is the matching probability of one column. In the DNA sequences, this is 1 over 4. In protein sequences, this is going to be 1 over 20. And then we are going to just set this left-hand side to 1. After you do that, you take the logarithm of both sizes. So 1 is equal to mnp to the L. If you take the logarithm, you're going to get L here. This is L is going to be equal to, or the expected length to expect at least one time, or not at least. These are all probabilistic. You may never observe it, or you may observe more than that with certain probability, but the expected number is 1, which means that you expect, if you see a matching run of length R in that case, this will not be unexpected. We should not get surprised. So in other words, for example, let's go to our example in which we have DNA sequences of length 5 and 300. So the matching run that we would expect in this case is going to be log 1 over P. The probability is 1 over 4 here. When the probability is 1 over 4, I'm in lecture. There's a note on my door. Since the probability P is 1 over 4, this is going to be log base 4. So log base 4, 300 times 500 is the length that we are going to be expecting. So we can actually do that. So log base 4, you can use actually. Do I have that here? Let me see. MATLAB log base n. Logarithm and MATLAB answers. Let me see that. You should be able to get that. Yeah, actually, to get any logarithm, we can, for example, I think MATLAB provides the natural logarithm and logarithm base 10. So if you want to get the logarithm base 3, you just need to divide these. Okay, so here, so all we need to do is, here, let's see, let's go back to this. It is, let's use a natural logarithm. So 300 times 500. This is the natural logarithm, and we are going to divide it by log 4, right? So it's 8.5. So here the expected, so if you got a matching run of length 8 in the case of DNA sequences, you shouldn't be surprised at all. Because if you have a DNA sequence of length 300 and 500, observing exact match of length 5 between in your alignment is something totally expected. Okay, between two random sequences, they may be totally random because the probability that we have here is totally random between totally random columns. The probability that they are going to be matching between two totally random DNA nucleotides is 1/4. And therefore, if somebody gives you two random DNA sequences of length 500 and 300, and if you're in your alignment, there's a matching run of length 8, you shouldn't be surprised at all because this is what is expected. Okay, so this is the analysis of matching runs. As I said, these are the actual number of places, n minus L plus 1 and n minus L plus 1 places to where the match could start, but it's roughly approximately this. We can also make this product to be equal to m times n. We can roughly, when m and n is larger and when the matching run itself is small, like 8, we can actually ignore this and roughly make it equal. Actually, in BLAST, there is a correction factor, some constant number that the e-value is multiplied with to basically remedy for this approximation to get back to its actual value.
Hocam,
yes. Yes, sure, please.
Bu hani probability olarak bakacak olursak bunların match ederken sliding window yapıyoruz ya, kaydırıyoruz. Bu sırada bazı parametreler üst üste çakışıyor ve mesela şöyle durumlar oluşabilir. Diyelim ilk birden fazla case oluyor slide ettiğimiz için. Bunların bazılarında bir şeylerin bir şey olmasını beklerken diğerinde olmaması gerekiyor. Bu yüzden birbirlerine independent olmuyorlar. O yüzden doğrudan bu şekilde Mn çarpı P diyebilir miyiz? Yani independent değil gibiler sanki.
Actually, the starting positions are independent because, I mean, if when you're sliding a window, that may be another alignment between two different parts of the sequences. The local alignment result, where it starts, it may contain some parts may be overlapping, but that's another experiment. It's like what you're asking is something like this: when you are tossing the coin 100 times, toss the coin 100 times and try to observe how many matching head run. Okay, for example, you're going to toss the coin 100 times and we are going to look at whether it's head or tail or head or tail. Okay, so here we are also, for example, we may need to wonder what is the expected value of a matching head run of length 8, again in this case. So am I going to have head, all right? So what you're saying is this. For example, I can, since these windows are overlapping, okay, so if there's a matching run of 9 heads, for example, this here is not independent of this part. So actually, in this case, you're right in the sense that here we have two matching runs. Since they're overlapping, we will count these as two separate head runs of length 8 each. If the total number is 9, 1, 2, 3, 4, 5, 6, 7, 8. Let's put another one, 9. If I'm looking for a head run of 8, since I'm sliding a window which is overlapping, it seems like these windows have some dependent parts with them. But we are not asking actually whether we have two matching runs that are close to each other, or we are not comparing two head runs. So in that case, these coin tosses, each coin toss is independent from each other. So when you toss the coin here, when you get a head, you could have gotten a tail here. But what you're going to get in the next coin toss is really independent. here. Oh, when the length. So let me first ask this question. Then I'm going to get to Burçak's question. But you may this sliding window and the overlapping window where we are trying the experiments may be confusing a little bit. But it's like, think about all of these windows of length 8, a window of length 8, an independent experiment by itself. And because we start a new observation at this position, at I, we start a new observation and we check whether we have 8 heads. At I plus 1, we just forget about our previous observation at I, and we start an observation at here. If we get another head at the end, it may be another version of, maybe another matching run, head run of length 8. But here, what is independent here is that what we have in this trial, a coin toss at step I, is independent of a coin toss at step I plus 1. Similarly, when you have 2 amino acid sequences, can you say, for example, if I have a match of VV here, okay, can I say what is going to come later? For example, if I have an A here, whatever my windows are, is this second position, second column, look at the second column here, this is the first column, it's a match. The fact that this is a match, does it affect the fact that this is going to be a match? It's still 1/20. So it's the independence assumption here is the matching of those individual columns. And the places that you can start really is, for example, one match may be here. I mean, these two may be matching with each other. So it's a quadratic, it's m times m, because any window of length 8 or 5 could be matched to any window of length 5 or 8 here. The fact that we are sliding is just we are performing more experiments. Maybe we just had a match and we started here. They're actually, since the independence assumption here is between these individual matching columns, and it doesn't change the number of times you can put the diagonals here. How many where the number of diagonals you can put here, still it's m times n. I mean, those are all sliding windows. For example, this one is an overlapping sliding window with this one. Look at these two diagonals. This diagonal is actually overlapping with this one in the other sequence. These parts are independent. But whether we have similar amino acid, the amino acid composition that are here, that amino acid composition is independent. We assume that. We also assume that in the alignment, because we have those scoring matrices that are applied independently at the cells. We assume the amino acid distribution or composition here is independent and constant compared to the amino acid composition here. So this place doesn't affect any place that are here. So the independence assumption is really at the single column level. And if you look at this, you could have put we would count them twice. We would count them separately. This one will be a matching run. This one also will be a matching one in those overlapping columns. You may still argue that, okay, it will increase the chance. It seems like since we have some matching here of length 5, it is possible to continue that. I mean, it seems like we already have a matching length of 5, right? It may be extended to the left and right to make it 8. We have a less likely, but this becomes a conditional probability, and that conditional probability will of course be higher, and our expectations will be higher if you're given that there's a match of length 5 already exists in the sequence. So this conditional probability may change our expectation, but without no conditioning, all the columns becoming independent from each other. This is actually the correct way to analyze with the just assumption of the individual columns being matching differently. I hope I tried to answer your question. I mean, there may still be questions that are not answered, but basically the sliding windows and their overlapping parts, only after you observe something, they may the conditional probability, if you think about that, it may affect the other parts. But if you just think about this as independent experiments, you can easily extend this one-dimensional coin toss idea. For example, if you don't know about anything about the previous window, you have found that there was no single match. For example, it may have been H, 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 and a T destroying the hedge-run of length 8. All right. So if you do that, for example, you may think that, okay, I already know that I have a T here. There's no reason to start another hedge-run here. I already know it's not going to be there. Okay, so but this is like since we have observed that this is T, this knowledge actually destroys our starting a new experiment here. But these are all separate experiments started all these things. So given that there is a T in position I plus 5, then there is no need to start these experiments. You're right, that part will be dependent. And when you're looking for these experiments, there's no need to start an experiment at these positions and at these positions. But before we know that there's a T here, we cannot make this assumption. This becomes, as I said, it's like conditioning on the knowledge that there's a T at that spot. Now, if the length of now getting back to Burçak's question, if the length of sequences MN becomes much more closer to the L, we don't ignore L in that case, but this rarely happens. In practice, the matching runs, for example, in BLAST, the matching run the exact match that they're looking for amino acids is length 3, and for DNA sequences is 11. When you're aligning two DNA sequences, 300, 500 are really small numbers. You usually align DNA sequences much longer than that. So usually this 3 and 11 is very small compared to these 300, 500, or 1000. And in practice, L really is smaller than M and N. So, and when you're trying to align smaller sequences and you're looking for largest matches between them, for example, if M and N is small, in that case you cannot ignore, and you have to put them in the equation too. Yeah, exactly. So, and also, yeah, that's also the case. Your second statement is also in line with this. If M and N are small, trying to find the longest match almost equal to their size is a very low probability. So it makes sense because in practice, really, in the case of protein sequence and DNA sequence analysis, the sequences that we align are much longer than the expected length. So the expected length is really small. If your M and N is small, like 50 and 30, okay, if they're 50 and 30, in that case, the expected length L still be very small, like 2, okay? You cannot set 1 is equal to M times N if M and N are small. If you take this log, again, if you multiply it with 1 over P, 1 over P is 1 over 4, not 1 over P, times P here, which is 1 over 4, P to the L. If you set this and try to find what L is, it's always, if these two are small, L is going to be even much smaller than that. All right, so they expecting at least once this match. If the sequences are short, L is even going to be shorter than that. Don't forget here, the length L is going to be exponentially smaller compared to this product. It's going to be log base 4 of these, so it's really small. Okay. So and in that case, we can always ignore this. But as I said, BLAST actually takes into account this approximation and tries to correct it by multiplying the final result with a constant. We are going to come to that. So if we have, actually, if you look at that, it's not so ignorable, right? I mean, if you look at this value when m and n is equal to 10. In DNA sequences, when m and n are small, the expected length is like 3.3. So it's like we're ignoring 100 versus 49. It's, I mean, 7 times 7, if you or 8 times 8. So it's like when the sequences are small, when we ignore the length L, which is going to be 10 minus 3 plus 1 is 8. 8 times 8 is 64. So it's like we're ignoring, we are making 64, we are exaggerating it to 100. But still, if you take the log, they're going to be close enough. So in this analysis, it may still be ignorable. Now, we are going to now extend this. We just talked about the length of the matching run. Now, after we talked about the length of the matching run, we now take our next analysis goal will be to extend this length of the matching run to scores, because we will have alignments with matches and mismatches. The first extension is how can we just introduce the scoring function instead of the length. So this is this is the next step you're going to take. If all mismatches receive a score of negative infinity, okay, observing some positive score means that we are still looking at a matching run. We are still looking at a matching run, but if right now we are looking at a matching run in which our match score is 1. Okay, our match score, a single match score, is exactly 1. What if matching of certain amino acids are different than the matching of other amino acids? Or before going into that, what if instead of if matching score of 1, I just increase the matching score to +3? So my matching length of 10 immediately is going to be converted into a score of 30. Okay, if all of the matches are still scored the same. But as you can see, it's proportional. So whatever I get here, as the score is some number larger than 1, the analysis that I did with the matching run is going to be similar to with just match scores of multiplied with some number. Now, here is what we are trying to figure out next. If we have matches and mismatches, what is the expected? So the expected number of matching runs is still roughly proportional to, you can, instead of the length, you can immediately put your score, whatever your positive score is. So the expected value of a score to be larger than or equal to some score x will be proportional, not exactly equal to, but proportional to this, which means that fixing, for example, x the same, you get a score of 80, for example. You get a score of 80 in a matching run. If the sequences are like doubled in size, both of them, you would expect the 4 times, it will be 4 times more likely if both sequences are doubled in size. You would expect to observe the same score of 80 4 times more, in 4 different, because it's like you can do the same alignment. It's like when the sequences are doubled in length, imagine a matrix and quadrupling it like this. So if this was my original, sorry, I did it. Let me just try to divide it in the middle. If this was my original sequences, if I double the size of both of them, if my expected value to find the score of matching run of this is let that score be S80. If I expect to find one such alignment in this region, if I double both of the sequence lengths, you would, as you can see, quadruple in size. So they're actually proportional, quadratically proportional to the expected value of finding such a matching run with a score of at least x. Okay, so they are proportional. And here in their 1990 paper, in their first BLAST paper, Carlin and Altschul, who are the authors of that BLAST paper, they developed the statistics. And they extended this just matching run by including also mismatch scores. But for that, they had to revisit what those scoring matrices mean. So we have a scoring matrix, Blossom 62, and PAM 250, for example. What do those scores mean? First of all, in order to perform this analysis, a scoring matrix, any scoring matrix should satisfy this property, which is the expected value of a random match. So Sij, S is my score of matching amino acid type I with amino acid type J. Okay, the score of a random match. If you just pick two random amino acids and look at the score, the expected value of this score should be negative. Otherwise, if this expected value of a random match is positive, it means that you can just arbitrarily make your sequences longer, just randomly random sequences of arbitrary length, and you can increase your score. Okay, but if it's negative, it means that just randomly matching them, you will expect a negative score in total, and making the sequences longer is not going to increase the score. Okay, because I mean, we are going to have the expected. If you're looking for a certain particular length of a region, you're just like our expected value. It's going to increase, of course, but the whole global alignment is not going to be arbitrarily long or arbitrarily large. Okay, so arbitrarily long random sequences will have higher scores because, just as our analysis shows, as they're longer, the expected number of getting a matching run of a certain score is going to get larger for them, but the scores are not going to get higher and higher just because they're long. Then there's a significant what we want is we want to get scores that are positive because there are some significant matches. So if this is not satisfied, our analysis also just boils down to nothing, because just imagine a region of sequences which are all mismatches. Okay, I'm not thinking this is not the same as trying to find some diagonals in that alignment. Just have those two long random sequences and provide a random alignment by randomly mapping random amino acid pairs on top of each other. So it's really a nonsense alignment. That nonsense alignment is going to get a arbitrarily large positive score because the expected value of two random one is greater than 0 in that case. Okay, but that's why we don't want it. We don't want just arbitrary mismatches all over the place. So if this and by the way, this is, if you look at this, how it's computed, the expected value. So this is actually a discrete random variable. The score of the domain of this. What is the score of aligning A and J? It's our scoring matrix, which can get 20 by 20 different values. Okay, and since it's symmetric, actually 20 by 20 divided by 2. But if I and J, and if you also consider J and I, amino acids, for example, isoleucine, leucine, and leucine isoleucine could be taken into account here in the scoring matrix. The expected value of a discrete random variable simply is the weighted average of the value that discrete random variable gets, weighted by the individual probabilities. Since probability of obtaining an amino acid type I and amino acid type J in that random column, these are two independent events, we can simply multiply. This is like what is the probability of observing randomly an amino acid of type I at the top column, at the top row of the column, and amino acid of type J at the bottom column. So, or you can also think about it like this. You have a bag of amino acids, okay, and you randomly draw one amino acid from the bag. What is the probability that it is type I? You put your amino acid back each other, or you have a second bag of amino acids which contain all of the amino acids in it, and you pull out another amino acid, and what is the probability that it's type J? Okay, so this PI and PJ here They are also known as the amino acid frequencies in nature, or the PI and PJ are not related to scoring matrices, like in the sense that, for example, if a certain amino acid is more abundant in nature, its PI value, this value is going to be larger. And if an amino acid is rare, like tryptophan, PJ is going to be lower. All right, so we need to, this expected value is considering all those amino acid frequency values in nature to compute the expected value of a random match. And it has to be negative, otherwise, with many mismatches, with lots of mismatches one after another, you would get a positive score otherwise, okay? So Carlin and Altschul actually converted the previous the score, the matching run being proportional to the score, turned it into this formula. You don't need to memorize any of these formulas. This just shows that the length of the sequences still matters. The longer the sequences, we would expect to get more alignments of at least score X. So X here is our row score. So this is basically saying that what is the expected value to obtain, what is the expected number of random alignments with score S or larger. And this K is that constant factor I'm talking about. And this lambda, so it's our probability just is dropped here. It turned into some e to the minus lambda x type of function. And this lambda is computed for a specific scoring matrix. Because we are going to now, I'm going to show how this lambda is computed next. Okay, so this K, which is less than 1 usually, is a proportionality constant that corrects the Mn space factor. This actually M minus L plus 1, N minus L plus 1. So this approximation is corrected by multiplying with this constant K. There are not really Mn independent places that could have produced this score. There are less than that. So therefore it's adjusted to a smaller number. Because we overshoot. By ignoring minus L plus 1, we make this product larger. Okay, so the expected value is actually overdetermined. It's not, we overestimate the expected value. This K less than 1 is trying to correct this. You may actually be arguing that how can this be a constant number, because L is going to be different from in every alignment. That number L changes. This is like heuristically, maybe they also found some optimal experimental result to make this correction. So this is just this proportionality constant is again determined by some heuristics. We can actually see what that K is. When you do a blast run, at the end of the results page, at the bottom of the results page, there you can take a look at the detailed parameters that were used for that, the details of the parameters that were used for that blast run. And this K is also described there, what it is, what that number is. But it has little effect on the statistical significance. This lambda is really important. It's also a constant that is used. It's computed for a specific scoring matrix. Therefore, when you're doing a blast run, for example, it allows you only to select from a previously computed scoring matrices. You can select Blossom 62, PAM 250. You cannot just input an arbitrary scoring matrix, because this lambda would have to be computed for that from scratch. Okay, so here this lambda is the fact that here we are going to talk about where this E comes from, but in the actual scoring matrices, Blossom 62 or PAM 250, the integers that we have here, they are not likelihood ratios actually. If they were likelihood ratios, we would directly be able to use 1 instead of lambda here. Instead, they are not actual probabilities of co-occurrence, but they are scaled version in order to make the likelihood turn into some integer scores. The developers of that scoring matrices multiplied those numbers by some constant. just enlarged, scaled all of them with a constant number so that they became integers or rounded integers at the end. But this lambda is that inverse scaling factor. So here is how they did in 1970s. Dayhoff et al. They use a limited set of families of the very few protein sequences were available back then, but they did a manual multiple alignment of these sequences like this and analyze. I mean, this is just a small example of what they did. They actually analyze a lot, many more. If you're interested, you can go ahead and read the original Blossom 62 or PAM 250 paper. But basically, they started with manual multiple alignments like this. So this is how there are some gaps here, but not too many gaps. So they're really highly similar known protein families, which are homologous. And after they do the alignment, for example, all the tryptophans here, WWWW, okay, or GGGGG, we all have, or leucine, valine, or I don't know what this is, but yeah, you see certain amino acids, PPP, and there's some mutation from N to D. So this was basically their way of looking at how nature prefers which amino acid could be replaced with what, and we still have a living functioning organism in evolution. So here, by looking at this alignment, I'm going to put this GIMP here and try to use this part. And because I want to also refer to this alignment here, maybe something like this. Now look at this. First of all, if this was the entire protein space, protein structure universe, I mean, these analyses will be much better if we are looking at as many protein sequences as possible and relate them as correct as possible. These alignments, if they are really correct and we look at as many protein sequences as possible, it will give us an idea about which amino acids are rare, which amino acids are common in nature, right? I mean, these are basically real protein sequences. If you see, basically what you can do is do very simple statistics. Look at the entire alignment. How many, for example, L's are there? For example, what is the individual probability of L? So in other words, I'm trying to make up my bags of amino acids. And in this bags of amino acids, I already know that certain amino acids are common. Maybe this G is really common. It occurs a lot, many more times than W. All right. So basically, you can just count how many L's are there and divide the total number of amino acids that you have here in your data set. Okay. So this is how this ratio can be used to approximate this probability. All right. So, I'm in lectures now. So what we do next is we need to compute this probability now. What is the probability to observe L, for example, and W together in an alignment column? So what is this probability? So it's this. If I select an amino acid from the bag, it's L, and I select an amino acid W, I select another amino acid from the bag after replacement, the second amino acid turns out to be W. So it's like to observe two amino acids of two different types in the same column. And we actually make this experiment for all pairs of, so we look at this alignment. So L and F together, this L and this F together. So all pairs of amino acids in a single column are like amino acid pairs that are observed together in nature. One of them can be substituted with the other. Okay, so the mutation occurred and there was a substitution from L to F, and this organism is still functioning. So these are like the scoring matrices are also called substitution matrices. So we see how the nature does substitution. So if we didn't know what nature did, the probability to observe, I mean, if nature just randomly matched these amino acids in a column, the expected probability to observe L and W together would be this, right? If you just randomly take out an amino acid and take another amino acid from the back, the probability that one of them is going to be L, the other is going to be W, will be this probability. Okay, so this is the probability to randomly observe both of them together. Now, we can actually count how many times L and W occur together in this matrix in a column. Just like we count L's, we count, for example, GNA. GNA occur once, GNA occur twice, 3 times, 4 times, 5 times, 6 times. Do we have another GNA in other columns? Yeah, another GNA. GNA occurs here, 1, another 1. So you just count by looking at the columns only. You cannot say, okay, GNA occurs here together. I mean, these two right next to each other, it's not considered GNA occurring together, okay? So this is not correct. So while we're counting, we look at the columns and see how many times GNA are occurring to substitute with each other, so they can occur in an alignment. So that number, again, so actually this is the PLV. The actual number of PLV that is occurring together, so it's not this actually, this is the random one. The actual probability of L and V occurring together is we count how many times L and V occur in this alignment and the total number of pairs in columns. Okay, so this one gives me the probability of they occur together as preferred by nature. Now, this ratio, now I'm going to show you something else. So this is the one I count by looking at the counting pairs of LV, and this is the one that I would expect by chance. All right. Now, if the actual count, so this is called the likelihood. Okay. So I'm dividing one probability with another probability. So this is the probability to expect these two L and W together by chance. Okay. And this is the actual thing that I observed. And this likelihood, they take the logarithm of this, natural logarithm of that, and it becomes our scoring. Actually, they multiply it with something, and it becomes our score. So it makes sense, right? I mean, if this one is larger, what happens if the actual number of observations is larger than this number, PLPW? Okay, so actually, when you say actual number, you multiply this probability with number of all pairs, and you multiply also with this number of pairs. Or when you look at these, you can also compare them as probabilities. If this probability is larger than this probability, we are trying to take a logarithm of something that is larger than 1. In this case, the logarithm is going to be a positive number. Okay, since these are probabilities, there are no negative values here. But if the numerator is smaller than the denominator, which means that the nature does not even prefer these together. Even by chance, randomly, L and W is more likely to be, I mean, if this one, if PL times PW is greater than what we observe in nature we don't observe these together at all, for example, then in this case, we will receive a negative score. So the positive match scores and negative mismatch, the mismatch penalties are exactly this log likelihood ratio. This log likelihood ratio has some problems when we have 0 observation, for example. The score then, the log 0, it will be log 0, which is going to be minus infinity. All right, so if PLW is really small, then this one, you may get minus infinity score. So they actually introduce some pseudo counts. They assume at least we observe all of them at least once to avoid this negative infinity values, but it's going to receive a very large mismatch penalty. So these log likelihoods, they are then I'm going to stop lecture in a couple of minutes, but they're then multiplied by some value. So this is the log likelihood that I was talking about. This is the actual probability. This is the probability of observing by chance. The scores here are actually, the similarity score is not this one. They're actually multiplied. The similarity score that we have is a multiplication of these likelihoods with some constant number, and this is what lambda is. All right, now I'm going to stop today's lecture. We're going to finish this on Monday. Okay, any questions? Questions? No? All right, so that's it for today. Thank you very much. Have a good weekend, everyone. Have a nice weekend. I will see you all on Monday, and we will continue on these slides. All right, I will stop recording now. Bye-bye.